Okay, so I was asked about Blitz-Saas-Fee relation today, and that's something that. So who is talking? I can easily use my spot. I don't mind. So if you want to talk, sure, go ahead. So I was asked about the already Blitz-Saas-Fee relation. There were a few slides that I skipped yesterday, no, not yesterday, on Thursday, because we were running out of time. So since I was asked about them, I'll show them. I get equipped with recording. Right, so Blitz-Saas-Fee relation, the existing relation in galaxies between what's called external pressure in quotes, and we'll see why quotes in next slide, and molecular fraction. Right, so it was discovered by Leo Blitz and Eric Rosolovsky in this 2006 paper, and then worked on later. So this is the external pressure versus the ratio of H2 to H1 surface densities on scales of many hundreds of parsecs. And they seem to correlate reasonably well. So those are average lines for different galaxies, and they all have sort of more or less the same slopes. There is some change in amplitudes though. Right? So what this relation actually is not a relation between an H2 fraction and pressure, because they cannot measure pressure. What they measure, in fact, is the density. And it's only modified by the stellar density, but essentially it's a gas density. And so in fact, what this Blitz-Saas-Fee relation tells you is just another way of looking at atomic to molecular transition. So when you do it in simulations in the model which covers the whole parameter range in dust abundance and radiation field, you find that this relation does actually depend on your environmental parameters. This is, for example, metallicity in this case, and different colors show the theoretical models. There's different radiation fields, and black points are actually measurements. And this is a slope of this relation, and the amplitude. You take a power load and split it into two parameters, the amplitude and the slope. And you see that they do change systematically with radiation fields and metallicities. So please don't use it as a God-given answer to all questions in the universe. It is not. Right? It will be different in the high redshift galaxies. It will be different in dwarfs. Okay, so that was a short piece on Blitz-Saas-Fee relation. And now that actually today we're supposed to talk about star formation. Today we'll talk about two things, star formation and feedback. And so my first part is about Gannicus-Schmidt relation. And so this is a great picture that shows you both Schmidt and Gannicus, and in fact shows you a few of the O's as well, of the players in this game. This is Leo Blitz, Alberto Ballata, Adam Leroy. I think that maybe there are other faces here as well. Okay, so before I proceed, right, so you go to conference and you say, okay, Gannicus-Schmidt law. So anyone calling it law at this conference will be kicked out, right? There's nothing more removed from the law, right, than this. There's nothing common. Right? There's law of Newton, there's Newtonian law of gravity, first law of Newton, right? But the Gannicus-Schmidt relation had nothing to do with that, right? It's not a law by any standard, right? So please don't call it a law. Right? It's a relation. So, why it's called Gannicus-Schmidt? This is a bit of history. So the first paper on the subject was this famous paper by Martin Schmidt in 1959, that talked about relating surface density of gas and surface density of star formation. And then there were two important papers by Robert Gannicus much later that sort of revived this topic. Right? That's why we call it Gannicus-Schmidt relation, to give credit both to Martin Schmidt, who was first in this field, and then Robert Gannicus, who was made this very important sort of revival of this whole idea. So before we proceed, I just remind you, it's something we already heard several times here. Right? So the question, what stars form from, right? And the answer that stars don't form from gas, right? Because this is the maps of H1 emission from THINGS survey, the H1 nearby galaxy survey THINGS. So the green stuff is actually H1. So you're looking at atomic gas. Right? And in the same survey, you have ultraviolet radiation that tells you where young stars are. Right? And you can compare the distribution of stars and distribution of gas. And yes, of course, they form in the same galaxies, right? So they're located in the same region. But otherwise, there is no relation between them whatsoever, right? So if I flip them back and forth, this blue and green don't correlate except being in the same place. Right? So they're very, very different. In fact, if you do a cross correlation, you'll find the cross coefficient is actually 0. Right? There is no cross correlation between them at all. So the stars don't form from gas. Right? Start from molecular gas. Right? So that's the story that Ralph and I repeated many times. Right? And again, this plot makes it very, very clear. And so what you actually see now is the star formation rate. So and this plot was really made clear by these things surveys. That was 2008, 2009. So this is the surface density of star formation. And this is surface density of atomic gas. This is H1, sigma H1 if you don't see it from the back. And this is sigma H2. It's a surface density of molecular gas. And you can see the surface density of molecular gas correlates with surface density of stars reasonably well. There is scatter here, which is a different story. But it correlates reasonably well, and actually it correlates in a linear way. I'll talk about this later. Whereas atomic gas basically doesn't correlate at all. So the same values of atomic gas surface density originally change in star formation. That's why the coefficient is essentially 0. Except maybe something happens with very low surface density. Again, it's a story I'm not going to talk about because I don't understand. So this is the only plot of what's called classical methylation that shows you surface density of star formation versus surface density of total gas, atomic and molecular. Both Martin Schmidt and Robert Gannicus in the beginning used this as a quantity of interest. And so the only plot that shows us gas together because it's actually a bad way to represent it. And the data here, the points, black points and triangles, is actually the original plot from Robert Gannicus 98 paper. No, not original plot, actually original points that were plotted by Frank Biggio in 2009. And the colored contours is contours of the stink survey. So essentially what the scour contours are is you take these two plots, right? And you want to plot star formation rate versus sum of those. So you basically take this one value and this value, add them up and plot them. So the next plot I'm going to show essentially is this plus this summed horizontally. Right? And then you get this kind of curved shape because the large surface density is entirely molecular, so you see this correlation. In the low surface densities, the gas is almost entirely atomic, so you see no correlation at all, or very weak correlation. And then this sort of transition between two regimes. And so the same happens in the simulations. It's again the same model for H1 to H2 transition I talked about 2 days ago. And again, if you look at the atomic gas, there is no correlation whatsoever. Right? You can change star formation rate by orders of magnitude. Again, this is total. This is star formation rate versus surface density now various phases of the gas. So the dotted line is atomic gas. The dashed line is a molecular gas, in which case you get a very good correlation, which may or may not be linear depending on what you assume for star formation in the simulation. And then the solid line is just again sum along this axis, right? So the solid line is this line plus that. And there's of course log plot, so then it's a and the hatched region around here is actually the scatter that you find in the simulation because of these properties of H1 to H2 transition, a difference in column densities, etc. at given surface density on small scales. Difference in small scale and in distribution on small scales at given large scale surface density. Right? So those are actually scale. This plot is made on, that's actually, should have put it right. So the way it's plotted is there's all this done on large scales because we actually compare with observations which have low resolutions. And so all this is done by averaging surface density of star formation and gas on scales of anywhere between 500 parsec and this one actually 500 parsec in observations. It's somewhere between 500 parsec and a kiloparsec. So yeah, each point on this say Cow distribution that makes those contours is a patch of one of the galaxies about 500 or 600 parsecs across. Right, and again, you can put them on top of each other, and they do agree pretty well. And they agree first in the general shape of this transition, because, as I said, it's just a transition between atomic to molecular gas, something hopefully we understand. They also agree in the scatter, actually. And exploring the scatter and this relation is the next frontier in this field. I won't talk much about that, but please be aware it's something that is actually important. And this scatter, as it changes with scale, does contain important information about properties of star formation in galaxies. It's something that we are sort of in the beginning stages of exploring this property of this relationship. So if you now think about this mathematically, right, that I find a convenient way to think about these relationships is with a quantity called depletion time. And it's not just me, I think most people now use it. So if I take the surface density of star formation, which is just time dependence, time derivative of the surface density of stars, right, and this time derivative due to star formation, because of course stars also lose mass, and maybe there might be other reasons why surface density of stars changes. But if we just take the one which is contributed by formation of young stars only, so we can write it as proportional to the surface density of molecular gas, and there is this factor that accounts for the helium that mixed in, just 1 over helium fraction. So just 36% of mass contributed by helium and heavy elements, because this is just really molecular gas, right? So just hydrogen. And then we divide by time scale, right? These are units of solar masses per parsec squared per time. So we divide by time scale, and we call it the depletion time scale. So if we wait, just take the equation and wait for this amount of time, we'll get a substantial fraction of molecular gas going into stars. So we can also write this equation in terms of volumetric density. Right? And to make my notation simpler, I'm going to use this mg to describe the density of molecular gas. So it relates to density of hydrogen molecules by this 1.36 factor, which accounts for helium, which is mixed in hydrogen. Right? So this is total density of total molecular gas. By the way, occasionally, especially some theorists, that they claim that this is the Gannicus relation and this is the Schmidt relation. This is wrong. Right? So Martin Schmidt never talked about volumetric density. He only talked about surface densities. Right? This is just a comment. So then this time scale, the depletion time, in principle can be a function of density or any other parameters. Right? And for example, very often used model in which the depletion time scale is proportional to the free fall time, in which case it is proportional to inverse power of square root, and the star formation is proportional to density to 3/2 power. I will talk about this. So the fact that we write it this way, there's no any assumption about what this tau SF depends on, just a way to represent things. Right? And of course, our change to now understand what this parameter depends on. So what I'm going to claim now is the way I wrote it is a very bad way of thinking about it. Right? So you see this very often in papers in cosmological simulations. I'm going to make a very arrogant statement, a bold statement, that we should not think it that way. Right? It's a bad way of thinking. And the reason for that is the following. Oh, actually, the reason for this is that, please. I don't know what's going to happen when I press. I don't remember if I have answers. Who knows the answer to this question? Why is it wrong?
Because angular momentum is not conserved.
Angular momentum is conserved. And if you have any doubts about this, yeah, I assure you that it is conserved in a closed system, right? And I can bet you anything, right? $1,000 right away that it is conserved. So the reason why this thinking is actually bad is because the density is only defined on particular spatial scale, right? So the density by definition is a mass over volume. If you have no volume, you have no density. So we often think about density as being property of some kind of point in space. And that's because, first of all, in textbooks in which we read, this is often assumed. And then, of course, our everyday experience tells us, well, the density of A in this room, right, is a property of this location, the density of the table, right, I can define at each point. But it's our bias, because in the mean free path for particles in the air, especially in the table, right, is very, very short. So and then we often deal with things which are quite homogeneous, whereas in space, things are not very homogeneous, as I think Ralph tried to persuade you. So whenever we talk about galactic scales, we should always think about density as defined over some particular scale, right? Because if we go to small and small scales, we get into distribution and variation densities on small and smaller scales. So the proper way of thinking about this is to first fix your scale. I'd say I'm interested in things on 10 parsec scale, 100 parsec, whatever, you pick up a scale, L. And then you average, you can think about this, and you take the whole universe and divide it into boxes of sizes L cubed, and then you average every quantity on this scale. So you define the rate of star formation as in those L cube boxes. You define the density as the mass of the gas in those L cube boxes. And then you can write this relationship. So in which case tau now becomes function of density averaged over the scale, and scale, and then maybe something else. And so when you go to different scales, in fact, you may have different towers. Right? And if you don't appreciate the scale dependence, right, you can get some other guy, and you're talking about 100 parsec scale, and they talk about 1 parsec scale, right? And we get to fist fight because our scales, actually, our values for tau are very, very different, and we cannot understand why. Right? But it's only because we're talking about different scales. So please remember that. This is an important point, and even most experienced practitioners in the field often forget about this and make some silly statements. So what it means is that if you think about star formation, you should really think at least in 2D. Right? Not as a function of density, but as a function of density and scale. I'm going to show a few of those plots. So this shows the scale, and this shows the density. Right? In this case, density I measure in particles per cubic centimeter from 10, 100, 1,000, 10 to the 4. Right? And scales from 1 parsec to a kiloparsec. Right? So the scales at which because more just care about star formation. Right. What? What?
Higher density related to smaller spatial scales.
I should, sorry.
Something like this, the other way around.
No, this is just okay, I didn't say what those red lines are, right? This is maybe it was I spilled red wine here. So again, if you think about tau as function of L and rho, essentially what we would like to do is to basically, in some sense, draw some contours here, right? So those contours are just random things, random shapes, nothing to do with reality. I'll show you what reality tells us, right, in a minute. But essentially, you should think about as drawing sort of contours on this plane and thinking about the star as being at least two-dimensional function. And in practice, it may be more than two-dimensional. There may be other parameters which are important. There may be a truly random element of this when we fix on a given scale, etc. So the things might be really complicated. But at least what I would like to do to convince you is that you should be thinking in two-dimensional way, not in one-dimensional way. Now, let's see if we can actually put some constraints on that pure observation. So we know that in things galaxies, on scales above, say, 500 parsecs, it's actually parsecs, not kiloparsecs, sorry. This depletion time is in fact constant and equal about 2 billion years. So this is a plot from things papers. This shows sigma H2 versus depletion time. That's a different plot from a Morrison paper that again shows the sigma star formation rate versus sigma H2. And again, this you see a linear correlation. And if you take depletion time and just take 1 power off, so it becomes flat. There is a scatter there, right? Remember, the scatter is important, right? It's not just a random observational error. Right? There is important information hidden in the scatter, which we may not at this point quite understand what it is, but that's something we should be exploring and studying in the next years. But if you just forget the scatter for now, then the depletion time, in fact, is essentially constant over at least 2 orders of magnitude in surface density of gas. Right? Which means that in this plot, the star formation rate versus gas density, the slope is linear. And that's true for things galaxies which are nearby large galaxies. So before we can see that, just a slight note, what is actually shown here is in fact a median. And so I don't know why observers decide to show the median value rather than the average. Because what physically is important is what if I take all my regions of say 500 parsecs with a given density, what's my star formation rate? That's what I actually care about as a cosmologist. But for some reason, observers often use the median values rather than the average values. Maybe because they don't trust the average values and the errors or something. So, but if you have something which is distributed log normally, which is roughly this distribution, right? So on log scale, it looks roughly as a Gaussian. I'm not sure how exactly Gaussian it is, but it's roughly kind of bell-shaped. Then your average and your median will be related through the factor that depends on sigma. And so it's not a very big factor, right? But you should be aware that it's there. Right? So very often you hear talks and someone says, well, my depletion time is 2.5 billion years, my depletion time is 1.5 billion years. And it's not clear that those are actually different numbers. You have to be careful because you have to check how they're actually defined. Is it a median, is it the average, etc. So we can now go with high redshift. High redshift, of course, it's much harder to observe molecular hydrogen and observe star formation rate. But there was a lot of progress in the last several years. It's several groups working on this. And this shows a distribution of, against the same Gannicus relation, star formation rate versus a sigma of molecular gas. In this case, it's 1.36 factors already put in. You don't have to worry about this. And what is generally found is that you find a relation which seems to be consistent with linear. Of course, you have many fewer points at high redshifts, and it's usually the whole galaxy, so it's slightly different scale. We're talking about scales of several kiloparsecs at least, because it's just 1 point per galaxy. But in general, it's more or less linear. It may be actually offset relative to the local relation. So the depletion times, people quote maybe 0.7 billion years, 1 billion years, etc. So they seem to be maybe different. But they, nevertheless, in this case, they're not very much different, and they're actually consistent with, again, constant depletion time. So whether those numbers are actually different or not, actually it depends on this Pandora box, this X-CLO factor. Because the only way to measure molecular hydrogen redshift 23 is through the CLO emission. So any observer who puts a point on this plot have to assume the X-CLO factor. So if you believe, we talked about these two different models that give different signs. If you actually believe our model, then in fact, we get this apparent increase in depletion times, and the decrease in depletion times, increase in star formation rates, simply because it's density dependence of the CLO factor. So from our point of view, this 0.7 at redshift 3 is the same as 2.5 at redshift 0. Whereas if you say, take Narayan's model, they would say it's significantly different. As I said, jury is still out. So, but I'm not going to take this difference very seriously. Right, so this again, this plotted on the same scale, and you see you get the same distribution. So that's the conclusion. Basically, whether the depletion time is different at high redshift or not is still an open question. Even if it's different by a small factor, right? So it's a factor of 2 or 3, which will be small over the several orders of magnitude and surface density, which we consider. So it will be sort of second order effect on how this depletion time changes. So now what I'm going to do is to try to put something that I know about on this plot, L versus rho, right? So we talked about Bigel and Genzel, and at this point I'm going to pretend this high redshift measurement, by the way, is a group led by Ian and Genzel. I'm going to pretend that they're consistent. Again, if they're not consistent, this factor of 2 inconsistency I'm going to ignore. Right? So I don't care about factors of 2 at this point. So essentially what they say is that when we go to large scales of hundreds of parsecs, this depletion time, I'm now plotting contours, right, is actually independent of density. This is a contour. So it says all the values in this blue bar have the same value as the depletion time, 2 billion years. At this scale, there is no density dependence. So your star formation is actually linear in density. This is just observational fact. Right? So I'm only going to show observations here. there is one other point that you can put here, and those observations of star formation rates in molecular cores. Right? So those are obtained by actually counting young stellar objects in molecular cores and using HCN as a tracer of star formation rate. And so what they find usually is that if you go to low enough density, there is no star formation whatsoever. There's a threshold there. But if you go to densities above 10 to the 4, the mass in young stars is directly proportional to the mass in gas. So again, the relationship is linear, except that the time scale there is not 2 billion years, it's 20 million years. So you have a threshold, first of all. You only form stars at high enough densities on this very small scales of individual cores. And then the time scale is actually very short, 20 million years. And then there are other people who make other claims. Right? For example, there is a very common standard, common ansatz used in simulations and galaxy formation and star formation models. Just assume the constant efficiency per free-fall time. So in terms of depletion time, it says that my depletion time is actually proportional to free-fall time with the coefficient of proportionality, which is in this language will appear in the bottom. Right? And again, in this case, it goes as 1 over square root of density, in which case, in a more familiar form, if we write it as a function for the density of star formation is proportional to the density of gas to 3/2 power. Most actually simulations that you've seen in this class use this assumption in this course. Again, remember, it's just an ansatz, right? There's no physical reason why you should want to put the free-fall time. The free-fall time is irrelevant if you listen to Ralph, right? So molecular clouds are turbulent and not freely falling uniform spheres. And so the free-fall time is actually not a physically relevant quantity here at all. So this is just an ansatz. Right? You just decide to to parameterize things that way. Right? It's your choice. But it has no physical justification. So it only becomes meaningful on really, really small scales where things might be really falling on a free-fall time, like cores. So if I now use this language, then instead of free-fall, instead of the depletion time, I will be talking about efficiency of star formation. So the reason why this ansatz is so popular is due to Kramhals and Tan, who in 2007 claimed that essentially observations require that. So what they show is this is density versus this efficiency epsilon that they called it SFR-FF, but it's the same thing. And essentially they said that all the measurements over a large range of densities is consistent with this efficiency being roughly 2% or so. If Ralph was here, he would actually claim that he had some objections to the statement because he claimed that the way they choose those points is not quite right, and so there's clearly an increase in these scales. But even if there is the deviation from that at very large densities, right, at least over a reasonably large range of densities, anywhere from 100 to 10 to the 4, or even beyond, it seems to be consistent with being constant. Which again, in this language, it means this quantity is constant, and so this will be a function of density in this way. So I can now go back and plot those measurements on my picture. However, if you actually look at what they've done, they looked at regions of different densities, but those regions of different densities also live on different scales. So you have giant molecular clouds, which sit to a density of 100, but those have scales of tens of parsecs. And there, in fact, the depletion time is 500 million years. If you now go to the high density regions, those are actually infrared dark clouds. Those have sizes of a few parsecs. So in fact, the Kramhals and Tans are not sampling only the density axis, they're also sampling the scale axis. So they're actually going along a line on this plane. Right? And the same, if you go even further, they will actually get the same point because it's the same data essentially. So what they're saying is that this 3/2 power law actually works along this line, but it's not a universal property of this plane. In fact, this is actually all what is known about the depletion time today. I am not aware of any other point I can place on this plot. If you do, let me know. So in fact, this picture is consistent with infinitely many forms of how depletion time may depend on those two parameters. In fact, it's,
Can I add a data point?
yes,
The central molecular zone of the Milky Way is central few hundred parsec, so at 10 to the 2 has an average density of about 10 to the 4,
yes.
and the depletion time scale is about a gigayear.
Depletion time, I think here.
Yeah.
Good, thanks. I wish you did, because you see what I'm going to do? One more click, okay? Right? So this is great, right? So pretend you said it after I showed them the next slide. So what Krampus and Dunn actually did, they tracked the depletion time along this line, right? So they convolved, they sort of folded this two-dimensional space into one-dimensional. And there the result is actually queried until at least we can argue whether it continues at higher densities, as Ralph was telling to me in private. But at least over this range, it's fine. Now, as you can imagine, I can make infinitely many models of this depletion time as a function of these two parameters will be consistent with this. Particular one which I like is this one. So this one tells you that the depletion time is actually independent on density on all scales, right? But only depends on scale. And so this is, again, this is just a scenario, right? I wouldn't even call it a hypothesis, right? This is just a think about this cartoon. But it just shows you the extreme cases which can be true. Right? So in this case, the depletion time is always density independent. You always have linear relationship with density on a given scale. But if you go to smaller scales, you have the threshold, and then the depletion time will decrease because if you have 20 million years depletion time in molecular gas, you only can have 1% of the gas in this regime, because this divided by z should be equal to that, right? We still have the same number of stars forming in the galaxy. So if you form stars 100 times more efficient in this dense gas, you only can have 1% of this gas being in this regime. Because you can take your galaxy and divide it into boxes of different scales, so it's this integral constraint. So the center of the Milky Way, you're saying it's how many parsecs? Yeah, it's somewhere here.
Yeah.
So in fact, they're actually consistent with this line being scale independent. Okay, I didn't know that, so I learned something useful. Again, please don't take it very seriously. I go around and make strong statements about this idea, but I am not going to bet more than a bottle of mediocre wine for that. Right? It seems cool, but I mean, I really have no reason to claim that why it should be this way. So what I'm going to say is that it's very important to think in this two-dimensional way. Right? And again, we don't really know what this two-dimensional function is. And one of the challenges we are facing right now is to really understand observationally put more points on this, and then theoretically understand how this function comes about and what it can be. And in fact, as I said, maybe there are actually more axes here. Maybe there's third, fourth, fifth, and whatever 10th axis. Maybe you should think in 10D rather than 2D, but it's something we're going to learn soon. So in summary, right, my conclusion about star formation on galactic scales. So this is not an option, right? You have to think that way. Right? If you forget about a scale you're talking about, you're going to make statements which may be wrong. Right? Because the density is only defined on scale. Density is, by definition, m over v. There's no v, there's no rho. So on large scales, we know the depletion time is independent of density, and that's a fact that is reasonably well established over different redshifts. Right? When I say independent, it still means that there may be some second-order effects where I say at redshift 3 is factor of 2 shorter, for example, but that will be a second-order correction to what our state of understanding today. Right? And there also may be differences in the fact I didn't have time to go. There may be some differences in, say, normal versus merger mode. Remember, there's ultra-luminous infrared galaxies which have different XCO factors. So they may actually go forming stars in a somewhat different way. So this constant efficiency per free-fall time, this 3 horsepower that most people use, is an ansatz. Right? There's no physical reason for this. A free-fall time is irrelevant in molecular clouds. They're turbulent going down to very small scale. So the free-fall time of the whole cloud is not a physical parameter that describes any physical process. They're not free-falling single entities. And there is this interesting ansatz, which you may keep in the back of your mind. Again, I cannot really bet that it's true, but it is consistent with all existing constraints. And so in reality, I suspect that reality is probably complicated, and this tau probably depends on both of those parameters in a somewhat non-trivial way. But that's an open question right now. So what I'm going to do now in the last whatever minutes I have is to talk about this new idea using the discussion set formalism and star formation. And Ralph already mentioned that, right? And I will try to explain it better. I don't have a very strong opinion about this. It seems cool. I'm not sure it's right, right? But let's see how it goes. So we know that the density distribution in simulations of supersonic turbulence is closely approximated by log normal. And this is just pictures from some of those simulations. This is an image from the simulation. And at least until we go to very high densities, we get something which is log normal. And so this idea, in fact, so whenever you have something which is normal, right, so it's log normal means it's normal Gaussian distribution of log density. Right? It makes you attempted to use pressure active formalism. So this idea we first started by Padon and Norland, as far as I know. Then Hannebert and Chabrier repeated it. And then lately, Hugh Hopkins wrote a whole series of papers where he extended this very far, right? And he made some crucial breakthroughs in this pressure active of idea. I'll call it excursion set formalism rather than pressure active because I think it's a better name. So it builds an analogy with cosmology. So Gaussian linear density field of large scale structure is replaced with a Gaussian log rho field of molecular clouds. And then just from a general principle, right, if you talk to a cosmologist, the first reaction, no, it cannot work. Right? And I know people who said it many times. So your naive expectation that no, it shouldn't work because Gaussian field of large-scale structure, linear field, is actually truly linear Gaussian field. Whether this has just Gaussian PDF, it doesn't mean it's actually Gaussian random field. So I'm going to give a very brief overview of what this excursion set formalism actually is. Right? So it's also known as pressure active. There may be a difference in terminology. Some people may call different flavors of it, but I'll just call it all excursion set formalism. Right? In general, it's more than pressure active. Right? So if you take a box of size L, right, some particular given one box in one particular place in the universe, and you have some field delta of x in it. So this field will be called random, right? If value of delta, right, in the same location in some other box cannot be determined from the corresponding value of delta in B1, right? So I have two boxes in completely random places in the universe of the same size. And then now I take quarter from this point, quarter from this point, and this box B1, whatever, my delta is 5. And now I'll go to the same box, to the same location, right? One quarter this way, one quarter that way, in some other place. And I measure value here, and its value is 3. And I go to a different place, and I measure it's exactly the same place, right? And it's now minus 10 or something. So if those are completely uncorrelated, then we call that delta is a random field, right? So its location in space, in this sense, random. So we can take Fourier transform of this delta. Right? When we still have no delta as a function. There's delta in every point in space, right? It's just that deltas defined this way are not related to each other. So I can take the Fourier transform, right? And then if this is a Gaussian random field, then the property of this delta, which is function of three-dimensional vector k, is entirely determined by the power spectrum. So the only information which is there is all hidden in the power spectrum of those of this Fourier, or the power spectrum of this field, which is the amplitude of the Fourier transform. So what it really says, if I take now two deltas at two different locations in Fourier space, two different wave numbers, I multiply them. I have to take one of the conjugate, and then I average over all possible vectors or all possible realizations. Or this average may mean different things. But if I just average it in some sense, what I get is a power spectrum, and then this delta function, Dirac delta function, which means that those two vectors, if they're different, then this average is going to be 0. And so there's no correlation between two different wave vectors, different waves. So that's what a Gaussian random field is, by definition. So if I now take this formula, right, what it tells me is that all the non-random information is in this P of k, everything else is random, So I can take this Fourier transform and reverse it. And I can write my delta as a function of x as the integral, is an inverse Fourier transform of a square root of p of k, because p of k measures the square of the amplitude. And then some random number lambda, which is truly random. It's truly random in the sense that if you take two of those numbers and average them, they're not correlated. Right? They're absolutely uncorrelated, two random Gaussian numbers with unit dispersion. Right? They're sometimes called phases, which is not quite correct. There will be phases if you write it as e to the minus I phi, then phi would be a phase. They should actually be called amplitudes, but that, there is some historic terminology here that stuck. And so then if I have those lambdas as random numbers, I can write this delta. However, depending on what this p of k is, this integral may actually diverge. So you may have a random field in which you cannot really tell what the value of delta is at this point, at any given point, at any fixed x, if this integral diverges. So in that case, what you can do is to treat it as a limit of a smooth field. Now, instead of going to delta, I can see the delta, which is smoothed on some scale r. And the smoothing can come through this function w, which is a low-pass filter. So at large scales, it's 1. At small scales, it's 0. And then somehow it goes from 0 to 1. And it can be infinitely many ways you can do that. So this integral will always converge because this one will diverge at large k. K goes to infinity. Integral from, if you convert it from 3-dimensional to 1-dimensional integral, it goes from 0. So unless p of k behaves really badly at k equals 0, then in fact it will converge for any p of k as long as this one falls off at large k sufficiently quickly. Right? So and this tradition is satisfied quickly enough. Then you can make sure that this one converges, so this one becomes a definite number, and then you consider delta at some point x as a limit of this smoothed quantity as r goes to 0. In fact, limit may not even exist. Right? But you can think about this at least in this sense. So the excursion set formalism then considers this delta at a given point x and some scale r, right, as a function of r. And it compares this with some kind of barrier function. Defines some function b as a function of r, right, for your goal. Right? So this barrier function depends on what you actually want to achieve, and I will show you the barrier functions for some examples. So obviously, this delta as r goes to infinity should be 0, because delta is a fluctuation, right? So when you average over the whole universe with infinite size, it means you just on only one patch infinite size, right? You get the average, so the fluctuation is 0. So as r decreases, then this delta x of r at given x, so we keep x fixed, right? For any x, this is going to be 0. Because you can take any point at the center of the universe and average over the whole universe, you still get mean density. So we take the fixed x and we change r. Right? So as r decreases, the delta will start deviating from 0. And then because it's a Gaussian random field, it will probably deviate in a random way. And then some value of r, it may actually cross the barrier. So what you start with delta equals 0, it starts going, or I should show you animation, so let's not use the board. So at some point, it may become large enough so it actually becomes larger than this b. And that's what we call the first crossing distribution. Right? So it's the first time this function crosses the barrier. It may cross more than one, and then cross up and go down. So it basically may behave in a very random way. But for excursion set formalism, what we care about is this first time it happened. Right? And first time it happens on some specific value of r because we start from 0. So what I'm going to show you is just an examples of this. It's a one-dimensional, not three-dimensional field. It's maybe a little bit faint, so if you don't see it from the back, just move closer. We already have high enough attrition rate, so there are spots here. So this is the same Gaussian random field. In one case, I have a smooth filter. This W function is very smooth. In another case, I have a sharp filter. So the W function is 1 above some scale and 0 below some other value. So it has it's like a step function. And then what I'm doing is just increasing r for given x. If I can get, if I can get my mouse. So if you increase r, you also have fluctuations become more and more. You're smoothing on lower and lower scale, so you get higher and higher fluctuations. And then the blue line is just this path from one particular value of x somewhere in this range, I forgot. So just one of those blue line, just one of those x's as a function of R now. I can do it again. So that's how Gaussian random field looks like. And so you see this delta as a function of I, sometimes called trajectory in this field. So if you, for example, you put a threshold say of 1, and you know that the blue line will cross this 1 at this point. And with the sharp filter, it looks more jagged. Because its filter is sharp, so then it's more random in some sense. But otherwise, it's qualitatively it looks similar. Right? And again, in this case, if we take a barrier of 1, so this trajectory cross the barrier at this point, and then down below the barrier, cross it again, and then depending on what your power spectrum is, it can do large number of times. The red is just delta as a function of x, and the blue one is also a function of r. I don't know what r is, because I didn't have it here. It's actually between 0 and 1. So that gives you some feeling about what those things are talking about different places on x, doing delta places in x, doing things like that, and then go down, up, and down. And depending on the field, you can make smooth or more jagged way, depending on what you define for W. That's your choice. Choice of your problem. So, for example, right, if we have this original projective formalism, and cosmology actually describes the collapse of system, in this case barrier, is just equal to 1.69, this linear delta at which top hat perturbation collapses. So you say I have a density field in the universe, and whenever my delta goes to 1.69, I know my top hat perturbation would collapse, so I should get a bound object. So that's how the projective formalism works to define mass function of dark matter Havers, for example. So in this case, the first crossing distribution becomes essentially 1/2 times the mass function of dark matter Havers, and this whole literature on this 1/2, right? It is probably the most explored number in cosmology. And then the mass of dark matter Havers is simply the average density of the universe times basically the mass within the sphere with this radius. But this excursion set formalism can be used for many other purposes, right? You don't have to define barrier this way. You can define barrier as something else, right? At some other threshold for some other process. For example, it can be used to describe reionization of the universe, where your barrier is a condition that particular region is ionized, for example. So Sash is around, so you can ask him if you find him about how to do the ionization. So in star formation, the excursion set formalism can be used for several goals. Right? First, you can think about this first crossing distribution. And so this first crossing distribution, if we can use it, right, will give you the mass function of the largest bound objects, in which in this formalism we assume that all molecular clouds are bound. Essentially, we can get the mass function of molecular clouds using this first crossing distribution. Then there is also something called last crossing distribution. Again, if you think about trajectory going up and down around this barrier, it may happen that it crosses it at some last point and then goes down. It does require some specific shape for the power spectrum. It won't happen for all power spectra, but for some of them, it will happen. So you might also have a place where it crosses last time, in which case you would get the mass function of the smallest bound objects, which will be molecular cores or even stars. And by itself, it can be used for many other purposes, because if you now go beyond just thinking about trajectories, but really using this x, which we didn't talk about, and think about x as a spatial location and try to map the spatial location to different trajectories, you can do things like studying distribution of holes in the ISM, clustering of stars, etc. So there's a lot of information there that you can extract. But then, of course, the question, okay, in cosmology, the barrier is just constant 1.69 number. So what should be the barrier B for star formation? So this is my quiz. Who's for A? Are you raising hand or not? 2? Who's for B? Okay. You see, if this is the test, right? This is the test how well people listen, right? So, because I did show the barrier. Okay? So it means that all of you except 2 didn't listen to my lectures. So this course is total failure now. You have to do it again, so let's stay for another week. It's this, right? The one I showed you, this dispersion relation for the stability. So if you become bound object, you have to be gravitationally unstable, right? And for a general disk with a finite thickness, this is n turbulence and the sound speed. This is the relation that tells you when this medium, right, which again, remember that in the limit when we consider scales much smaller than the thickness of the disk, then our disk becomes actually a continuous three-dimensional medium. So this is the most general dispersion relation that describes disk, uniform media, everything, turbulence, sound speed. And so this one can be used as your threshold, right, as your barrier. So all you have to do is to express this k in terms of r, right? But k is 2 pi over r, and make sure that omega squared equals 0 is then as a barrier for your perturbation. So this is actually the collapsed the barrier in this case. This is the condition that things become gravitationally unstable. So if you do that, then you can use this excursion set formalism, the theory of star formation. As I said, it makes very different predictions, essentially analytically. They're not quite analytical. In some cases, you have to actually do a Monte Carlo calculation, but it's not a real simulation. Right? You just run several thousand of trajectories, and that's all. And then you get a large number of variations, of relations correctly. For example, this is the mass function of clusters. And you get the black line is this predicted analytical, well, extended perspective, not analytical function. There's some measurements. There is a Milky Way LMC M33. In all cases, for the 3 different galaxies, you get a very good match to the observed mass function of molecular clouds. This, in fact, is actually IMF. And there are different IMFs in the Milky Way. Not exactly IMFs, because strictly speaking, the smallest bound object will be a stellar core, not a stellar mass. You have to make one jump there and say what fraction of this core goes into a star. But if we just take the core mass function, then this is measurements from the Milky Way from different star-forming regions. And again, the solid line is what you get from the extended pressure. You get terrific match. Then you make some very interesting predictions that actually IMF, or strictly speaking, the core mass function, would actually vary significantly at the low mass end, depending on what kind of disk you have. So it depends on the Mach number of your turbulence. And also depends whether, slightly depends on the power spectrum, whether it's 5/3 or 2 the slope. Again, but you do get this salpeter slope at large masses, no matter what parameters are. And then you get variations in low masses, at low mass end, which are in fact, there are some observational indications that IMF does vary at low mass end substantially. So why this works, none of the cosmologists understand, because in cosmology, the linear density field is a true Gaussian field. Here you have log of density is Gaussian, but Gaussian PDF doesn't mean it's a Gaussian random field. You can have something which has Gaussian PDF and being completely non-random. So why it works in star formation at the level of this is completely not understandable from a cosmologist point of view. Right, Ralph already left, so he cannot explain, but you maybe should call him or whatever. But again, why it works is unclear, because normally it's not. You don't expect it to be random enough for this to work, but the fact that it works probably means that it may be random enough. But again, I don't have an explanation. So what I want to tell you is that this is essentially a new, I don't know if it's a new subfield of star formation, at least definitely a new direction at looking at star formation on galactic scales, and even on very small scales, right? You're actually going to the core scales, and it still works there in some very non-trivial way that works surprisingly well, much better than it's supposed to. Okay, so let's, I think this is all for star formation. Let's take a break. Right? It already was an hour and a half of non-stop lecturing. Let's take a coffee break, and then we'll finish with the feedback, the last piece of this. Yes.
So I invite you to move to the second floor. We take the picture just in front of the building, in front of the Pepino a restroom. I'm not quite sure about the best way to do that. Either you